Hello, this is Professor Keen, and welcome back to Electricity, Magnetism, and Light. We are starting into Chapter 6 in A Student's Guide to the Great Physics Texts. This chapter is titled Coulomb's Law. In my previous lecture, I gave a short introduction to Charles Augustin Coulomb, who lived at the end of the 1700s. He was working at the end of the 1700s, beginning of the 1800s. Most notably, he developed what's called a torsion balance, which is a device that's able to measure forces with exquisite accuracy. He then used this device to measure the force between electrical charges. So what I want to do today is explain his experimental apparatus. So let's take a look at the text. This is on page 67 in A Student's Guide to the Great Physics Texts. And on the about the third page of this, he talks about the construction of the balance. This is on page 69. And I have blown up a diagram here that he has on the next page, page 70, but he describes it on page 69. So what I want to do is kind of walk you through the different parts of this apparatus and make sure we understand exactly how this is built. This is a wonderful piece of equipment that he designed, and it's going to be important for two reasons. First of all, to be able to understand his experimental technique and the reliability of his results, but also because we are going to be this week working with a Coulomb balance very similar to this one, not exactly the same, but similar to this one. We are going to try to reproduce these results that he carried out. Okay, so here we go. He says, I've learned by experience that to carry out several electric experiments in a convenient way, I should correct some defects in the first balance of this sort which I've made. Nevertheless, as it is so far the only one that I've used, I shall give its description, simply remarking that its form and size may be and should be changed according to the nature of the experiments that one is planning to make. The first figure represents this balance in perspective, and the details of it are as follows. So this is probably, some version of the experiment that experimental apparatus that he designed. He's probably been refining this for some time. So he has this glass cylinder, A, B, C, D. So I'm going to point to it over here. Notice here's A, B, C, and D. So this right here is a glass cylinder that he's using. And it's 12 inches in diameter and 12 inches high. And you put on top of this a glass plate that is 13 inches in diameter. That's the cover to it. This entirely covers the glass vessel. This plate is pierced with two holes of about 20 lines in diameter. So the two holes are right here and right here. Now, what does he mean by a line? Remember, this is in the late 1700s. So there were many different systems of units that were being used at this time, just like there are today many different systems of units. But today, most scientists or many scientists use some version of the international system of units. At this time, they were using kind of a combination of the imperial British system, other local systems of units. And so a line is a measurement of length in this older system of units. I looked it up because I wasn't quite sure what a line was. It's an unofficial imperial measurement, British Empire measurement, unit of length. It's about 1/4 of a barley corn. So there you go. I hope that helps you. If you think about a barley corn, it's about 1/4 the size. It ends up being about 1/10 of an inch or so. So if it's 20, if it's 20 lines in diameter, if it's 1/10 of an inch per line, this would be about 2 inches in diameter, roughly. One of them is in the middle at point F, you see right there. And you place on this a glass tube that is 24 inches high. This tube is cemented over the hole at F with cement ordinarily used in the electrical apparatus. At the upper end of the tube at point B, that would be up here at point B, so he has kind of a zoom up of the tube. This is point B, I guess. Oh, no, I guess this is probably a typo. This is probably at point B. It's probably my mistake. It should be B in the text, but it's H up here. At point H, I would say, is placed a torsion micrometer, which is seen in detail in figure 2. So this right here is the torsion micrometer, which is zoomed up over here in figure 2. Okay. The upper part, which is called number 1, that is up here, number 1, carries a milled head B, the index IO, so here's a milled head that's basically built on a milling machine perhaps, and an index bar IO, and the clamp Q, which is right here. This piece fits into the hole capital G of the piece number 2. So this is the hole, and it fits into right there. This piece number 2 is made up of a circle, AB. So here we go, AB. This is a circle around the outside here. Circle AB. And this is divided on its edge into 360 degrees. So there are markings all the way around. And the point is that this thing right here is going to be able to twist, and this indexing mark at O is going to point to some degree measurement right here as you twist it in there. Jumping ahead a little bit, there's going to be a wire hanging down here, and when you twist this, it's going to twist this wire from which something is suspended, okay? And how much you twist the wire is going to be indicated by this scale right here. Okay, so it's divided on its edge into 360 degrees, and there's a copper tube, Greek letter phi, okay, so this is it right here, that's a copper tube, which fits into the tube H, okay, so here's the tube H, and this piece right here fits into the top of it. Okay, oh, I see, I take it back. So this is tube H right here, it fits into it, that's number 3, which is then sealed to the interior of the upper end of the glass tube or column FH right here. So we've got this glass tube, and this piece right here, capital H, is fitted into this glass tube at the top of figure 1. The clamp at point Q right here is shaped much like the end of a solid crayon holder, which is closed by means of the ring Q. Okay, so there's like this kind of clamp right here. And in this holder is clamped the end of a very fine silver wire. That's shown right here, this silver wire. And by the way, that is what's hanging down the center of this tube, and it's going to be suspended. It's going to suspend this vein right here at point P, and which he'll be probably saying something about that in a moment. Okay, fine silver wire. The other end of the silver wire is held at capital P, there you go, in a clamp made of a cylinder, PO, of copper or iron with a diameter of not more than a line. Okay, so right here, this is another view. This is figure 3. This is this thing right here that is hanging from the bottom. All right. And the upper end, capital P, is split so as to form a clamp, which is closed by means of the sliding piece phi. Okay, so this is phi right here, sliding piece, which is used to kind of go around this clamp and hold this wire in here. This small cylinder is enlarged at C, okay, right here, and a hole is bored through it, so there's a hole going through it right here, in which can be inserted the needle AG. So there's a needle right here that goes through it, and you can see that hanging down right here. Okay. Let's see. The weight of this little cylinder should be sufficiently great to keep the silver wire stretched without breaking it. The needle that is shown in figure 6.1 at AG suspended horizontally about halfway up in the large vessel which encloses it is formed either of a silk thread soaked in Spanish wax or a straw likewise soaked in Spanish wax and fixed off from Q to A for 18 lines of length by a cylindrical rod of shellac. So in other words, you've got this stiff insulating material that is hanging right here. So it's insulating. That's going to be an important point because he's going to charge up this sphere at the end, and he doesn't want whatever charge you put on this to leak down this rod. He wants to maintain whatever electrical charge you put on it. Okay. At the end A of the needle is carried a little pith ball. That's just think about a little cork ball, 2 or 3 lines in diameter. And at G, the other end, there is a little vertical piece of paper soaked in terebinth, which serves as a counterweight for the ball A and which slows down the oscillations. So in other words, what's going to happen, let me jump ahead once again, he is going to charge up this ball that's kind of hanging down here, and then he's going to charge up ball A, and they're going to repel each other, and when they repel each other, this wire is going to twist like this. This counterweight at G is going to prevent this ball from falling straight down, so it's kind of balancing it, and because it's made of paper, if this thing swings away and then it kind of swings back a little bit, the air resistance on this will keep it from oscillating for too long. So it's kind of a vein that damps out any kind of excessive motion. or slows down these oscillations. Okay, I hope that's making sense so far. So we've been talking about this apparatus. Let me see if we want to go to the next page. We've said that the cover at AC was pierced by a second hole at position M. Okay, so over here, there's a hole right there. In this second hole, there is introduced a small cylinder, M phi T. So right here, M, Greek letter phi, and T, I guess he's going to call that ball T, the lower part of which phi T is made of shellac. Again, that's an insulating material, so that when you charge up this ball, the charge does not leak down right here, or rather up along that rod. At T is another pith ball about the vessel, so another pith ball. About the vessel at the height of the needle is described a circle ZQ. Okay, so notice here there's a circle around the glass. You might think of this as a piece of paper that's going to be marked off, and he's going to use this to measure the angle by which this vein in here is twisting. Okay, so at the height of the needle is described a circle ZQ divided into 360 degrees. For greater simplicity, I use a strip of paper divided into 360 degrees, which is pasted around the vessel at the height of the needle. Now, to arrange this instrument for use, I set on the cover so that the hole, little m, is practically corresponds to the first division of the circle ZOQ traced out on the vessel. So he kind of twists this lid so that this hole, when you hang this ball down, it's right around the 0 degree marking on this outer scale. I place the index OI of the micrometer, so this index right up here of the micrometer, on the point O of the first division of the micrometer. So it's going to mark out the first division right here. I then turn the micrometer on the vertical tube FB, okay, so or F, we might say FH, I think again I've mislabeled that. That he turns the tube on that vertical tube, turns the micrometer on the vertical tube FH until by looking past the vertical wire which suspends the needle and the center of the ball, the needle AG corresponds to the first division of the circle ZOQ. So in other words, he's kind of twisting this until when he's looking, you might imagine he's putting his face over here. This is his eyeball, so he's looking right here. And when he looks at it, he's looking straight down this line like this, and there's a marking right here, and that is going to be the appropriate marking. Okay, so that's going to be the 0 degree marking. I guess he says, I turn the micrometer on the vertical tube FH until by looking down the vertical wire which suspends the needle and the center of the ball, the needle AG corresponds to the first division of the circle ZOQ. I then introduce through the hole M the other ball T, suspended by the rod M phi T, in such a way that it touches the ball A, and that by looking past the suspension wire and the ball T, we encounter the first division O of the circle ZOQ. So he's going to touch this, and again, this is he's looking down, so he says the first division right there. Okay. I then, let me see, where are we at? The balance is then in condition to be used for all of our operations. As an example, we go on to give the method which we have used to determine the fundamental law according to which electrified bodies repel each other. Okay, so in the next section, he's going to talk about the experimental procedure. Let me just give you a quick intro to what he's going to do, and then we'll talk about that next time. Again, he's going to charge up this ball T. He's going to charge up the ball A by contacting them together. This is going to swing away, and he's going to use this torsion wire, how much you twist the torsion wire in order to keep it at various locations. He's going to use that to measure the force of repulsion between those two balls. And again, the reason he's using a torsion wire is because the torsion wire exerts a very, very small restoring force, you might say, or a force pushing back. So by twisting that micrometer by a little bit, you can apply very tiny forces of twisting forces. And in turn, you can then measure very, very small forces. Okay, let's stop there, and next time we'll go into section 6.2.2 on his fundamental law of electricity and the experimental procedure.